Hello, we are Sweetie. Today, we will talk about multi-echo MRI reconstruction, iteratively refined zero-shot spatio-temporal DeepGenerativePrior. Magnetic resonance imaging is an effective auxiliary diagnostic method in clinical medicine. MRI is a medical imaging technique in radiology to form pictures of the anatomy and the physiological process of the body. However, it has always suffered from the problem of long acquisition time, because it is necessary to read voxels one by one. The MRI data consists of the total of 32 coils, and their size is large. For example, if you take a picture with an RGB camera, not all pixels are taken at once, but one pixel is read one by one. Therefore, in order to increase the speed of MRI, not all voxels are read, but voxels are read by space without reading the voxels in the middle. So, MRI is acquired as a lost K-space. K-space can convert it into MR image by Fourier transform. K-space can be converted into MR image by Fourier transform. In other words, to reduce acquisition time of MRI, we reconstruct K-space images. There are MRI reconstruction methods, typically non-training based algorithms and training based algorithms. Many studies have shown that training based algorithms perform well, but require a lot of dataset. So, this paper proposes an improved reconstruction method to solve the problems. The method uses deep generative neural network and an existing method, SENSE.
Before explaining this paper, I will be talking to you about SENSE, a traditional method used for MRI image reconstruction. SENSE is an abbreviation for sensitivity encoding proposed in 1999 and is a technique using multiple receiver cores with different spatial sensitivity. It has been mathematically proven that images taken with multiple cores can be used to obtain empty information. Empty information is not filled in through any rule, but is obtained using hardware-acquired information, and the original image is obtained through this. SENSE is implemented using the following formula. I will explain the elements of the above equation one by one. Here, Y is reduced data obtained by photographing except for some frequencies. X is the unknown value, the original image data that we want to obtain from this expression. Next, U is the corresponding sampling frequency information used for undersampling. C stands for core sensitivity map by core. The MRIs can start with multiple cores placed relative to the subject. MRI scans typically use about 32 cores, resulting in 32 identical images with different contrast. Depending on the distance from the subject, each image appears as a black and white part, such as that image. Like this, the sensitivity is different for each core, and this is the core sensitivity map. Finally, the F function is Fourier transform. Although we will not elaborate on this concept, we will understand that the application in MRI is a one-to-one transformation that converts from spatio-temporal images to frequency signals through Fourier transforms and find the upside process through inverse Fourier transform. It is clear that the result of multiplying the original image X by the core sensitivity map and multiplying the sampling frequency by applying the Fourier transform should be the same as the Y. Eventually, all values in the expression except X can be obtained from the hardware, and the original image X can be obtained by applying L to norm using the fact that the two values are the same.
Now, I would like to talk about the image reconstruction method proposed in this paper. First, update the multi-echo image created by the GNN. Next, train and fine-tune the GNN parameter using this multi-echo image. Through this process, the sampled image can be reconstructed. Now, let's move on to the formula. First, put noise C as an input of sense. The output is the target of the generator. The output image of the generator can be optimized with X. Repeat this process to continue optimizing X and theta. This process allows you to obtain reconstructed images X from the sampled frequency data Y. As you can see from the picture, the MRI has improved significantly to a high-definition image. This is one of the advantages of the reconstruction method proposed in this paper. The second advantage of the proposed method is zero-shot. Zero-shot does not require external learning data. We can save money and time by eliminating the need to collect MRI data. Also, models trained on data can suffer from hallucination problems. Learning from the data of a sick person is likely to be rebuilt with the MRI of a sick person, and learning from the data of a healthy person is likely to be rebuilt with the MRI of a healthy person. You can prevent this from happening with zero-shot learning. To find out the reconstruction performance of the proposed method, we conducted an experiment. MRI obtains data from frequency, and our method only measures the frequency 1/16 to shorten the MRI acquisition time. This masked image, white spots correspond to the obtained frequency, and the black spots are the unobtained region. First, the initial image is created with the measured frequency using the sense technique, and each 5 images are taken at different times. The structure of the proposed method is as follows. There are 4 types of layers composed of convolutional layer, convolutional transpose layer, and ReLU. And our proposed method's structure is stacked in 6 layers. Through this GNN structure and iterative reconstruction process, the initial naive reconstruction image becomes more and more similar to the gold standard. Experiments were conducted with various epochs, and Epoch 15 resulted the lowest NRMSE, which was 0.08. In one epoch, GenNet is repeated 2001 times, and the loss value is printed out every 200 times. We can investigate the trend of change in loss value within one epoch. Through this, we can learn that there is oscillation of the loss value, but it can be seen as the loss gradually decreases as the epoch progresses. If you look at the MRI result for each step, the initial reconstruction uses the sense method. After that, the proposed multi-echo reconstruction with DeepGenerativePrior is used with Epoch 15. And you can see that it's gradually becoming a high-resolution image. As a result, we can obtain an advanced result by using our proposed method than by using existing sense method.
MRI has always suffered from the problem of long acquisition time. We can obtain an advanced result image by using our proposed method than by using existing sense method. This work proposed multi-echo reconstruction with zero-shot spatio-temporal DeepGenerativePrior, which is an iterative process of 1. Training the generator network using reconstructed multi-echo images, and 2. Updating the reconstructed images using the GNN output as a prior. The training of GNN does not require external training data, which is advantageous because obtaining a large set of multi-echo MRI can be particularly difficult. The experiment results suggest that the proposed approach can be promising for accelerated multi-echo MRI. That's all I have prepared for you today. Thank you for listening.